2? Was it easy, doable?
Average.
Average, okay. Like, what was like? Was it questions were difficult or like preparation uh, material was less? What was the main feedback for the quiz? I'll convey it to the other team members as well, right? If you have any feedback.
Sir, preparation.
So
Okay,
according to the content, I felt that something was missing on my part. Like I
okay.
felt that I have something maybe I read less, or I was found at like less peak point to answer the questions. Few questions, not all.
Got it.
Yeah,
Like,
so that was
uh, I felt like the questions were easy. Like most questions were easy, but uh, the graded assignments or like the mock questions or the practice questions, they weren't true to the actual questions that were being asked in the quiz.
Okay, so
Like there
were
was a
the assignment questions easier or were the quiz questions easier?
assignment. I will say
Uh,
assignment.
Assignment
assignments
was
are way
easier.
easier compared to
Okay,
quiz.
assignment was way easier compared to the quiz. Okay.
Like if I give
Like
a
not for all
like
questions, but
yeah. So
there were
if I say give
questions
a
that were way hard.
So if I give us at a just like this was more of mixed of mathematical plus conceptual patterns. Like it
Right,
was good. I will say it's a good paper, tough
right,
but good paper.
right. Okay. So what we'll do is for end term, what I can suggest is that every live session, I can give you a few questions from my side, which from the next week, since you were saying it, there was a gap in the level. So some practice questions, a little tough only. So you can practice them, and then in every next session or maybe in a TA session, you can take up the solutions for those questions. That can give you some additional practice for week 9 to 12, right? Apart
Fine,
from the
sir.
yes,
PHGs.
sir.
Yes, sir.
Yes.
Do we have all the weeks contents are there?
Week
11.
11 is there. 12, I'm not sure, but I think we have some content for 12. 11 is there for sure.
Uh,
12, probably some content is there for 12.
okay. Already it is discussed, I think. No, like solve with the session or GAPA discussion session. Nothing happened, right? No, not deeply. If
For
we
which week?
have doubts, for all the weeks, there are no GAPA discussions. No, only when we have doubts, we are discussing. No.
Yeah, actually, GAPA, the problem is that the instructor sessions they get streamed end to end on the YouTube channel, so that is why the GA cannot be discussed. But the TA sessions they can discuss the GAs. That is allowed in the TA sessions. In instructor sessions, we can give you like if you after the GA deadline is over, we can discuss the hints and all, but we can't solve it because the assignment gets repeated right across terms. So that is actually an issue. If it's recorded, then the solution will be there, right, for the next term students. That is why we are not allowed to discuss the GAs. But in TA session, you can discuss because they can stop the streaming and discuss with you. That is okay after the deadlines.
Okay,
Okay,
some
so
practical questions, if we do in another 2-3 weeks, it will be better.
okay, sure. Like what I'll do is today, since I got your feedback right now, I'll give you a few questions on discourse today because I have not prepared any extra questions for this week because I didn't have that feedback. So I'll give you on discourse just like I gave after the quiz, after the revision session last week. Then from next week, what we'll do is those questions we'll discuss first before beginning the session. And at the end of the session, I'll give you three, four more questions extra, little tough from my side. Then you can practice and we again discuss it in the following week. That will give you some extra practice of the questions.
Okay, sir.
Okay.
That will
Because
be good.
week 9 to 12 is very important actually. It is the most important weeks of the 9 to 11 at least. 12, I'm not sure what is there in 12 because we've not received the content yet. But 9 to 11 is extremely important. Okay, because that is actually the foundation of many courses in your degree level as well. So that's why you can expect a lot of variety of questions as well from these weeks.
So I found one thing in the week, I saw something like there was deployment to Hugging Face. Like we will do some real world applications or what?
In which week?
Week
In week
11, I
11,
think.
right?
Hugging
You
Face, yeah.
won't be doing any deployment. You will use existing models to test out some pipelines, right? For example, machine translation. In week 9 and 10, you build and scratch, encoder, decoder from scratch to do translation. In week 11,
Yeah.
we'll use a model in Hugging Face and see how that can be actually done in just 4 lines of code. It's like that. You won't deploy
Okay.
anything. You'll just test Hugging Face pipelines in week
Yeah,
11.
fine, sir.
Yeah, that is actually very useful also because in the real world, when you work with many of these things, you don't have to always fine tune and train from scratch, right? You can use existing things which are pretty good. So that's why week 11 shows you that aspect. 9 and 10 show you the training and fine tuning aspect, the scratch one, which we are following for the entire course. Mostly in the course, we have done from scratch everything, right? So same thing we'll do for 9 and 10 as well. In degree level, you
So,
get deep learning practice. In that, everything is done using Hugging Face. There, you don't do anything from scratch. So that is why in this course we have showed it from scratch how things work from scratch. But introduction to Hugging Face is also there in the upcoming week. That is fun. You will like that.
Sir, today you will be discussing week 9.
Week 9, yes, yes, week 9.
Okay. And sir, just last thing. If I have any problem regarding NPP marks, then like, will it be solved? Like,
You tell me the problem. I'll just tell it to Levin sir because NPP marks is completely with Levin sir. But I'll inform him. You tell it to me what the
yeah,
problem is.
I filled the description, this form, description form.
Okay.
Yeah, the discrepancy form. Yeah.
Discrepancy. Yeah, yeah, yeah.
Huh.
Got it.
The problem is they said that I have not used the track IO and I have also not fine tuned the model
Acha, I
from
think
scratch.
I have you raised the query on Discourse, right? So I think some TA saw that query and they have told it to sir. Sir is looking into it probably. Was it you only who wrote it on Discourse?
Yeah, I put with the photo.
Yeah, yeah, yeah. We have your query. Okay, so I saw it in the group also. The TA has taken it and he has told it to Levin sir. Sir is looking into it. So it will get addressed. Don't worry. We will
Oh,
solve it in 1 or 2
okay.
days.
Okay, because I have bad experience with TDS, so that's why I'm little more worried. So that's why I'm.
No, no, don't worry because actually instructors are busy. Let's speak with some Vivas, so that is why
Mhm.
maybe this week it will not happen, but on Monday onwards they will come to resolve these. Okay, so don't worry. Next week
Okay.
we'll do it.
Thank you very much,
and
sir.
sir, also I have added the track you part. It will showing I have not added.
Don't worry, don't worry. Track IO queries will be solved next week. Okay, but I'll tell it to sir again. Sir was also busy with Vivas this week. All of us actually were busy with some Vivas, so next week we will solve it out. Okay, so
If we fill the discrepancy form, that is okay, no?
yeah. You should fill that. Okay, anyone
Yeah.
who has any problem, just fill the form so that we get your data, and then next week onwards we'll just sort it out one by one. Okay, and get your marks updated based
So
on
Okay,
that.
sir.
what is the average marks that everyone like the NPP in marks? What is the average
I
marks?
don't know. I don't have the result form. I have not seen it, but I think it is decent as for what I have heard. It's not a bad. It's a good performance overall.
Yeah. So
Sir,
that
next
was
time, yesterday, Levin sir said that they will add bonus, something like that, not penalty.
Yeah, I think because there was this actually the course is slightly heavy, right? So that is why some discussions were happening on how to make it slightly better, like on the easier part for the scoring. So maybe they will add some things next week. Sir
Yes,
might be
sir.
knowing that because actually, see, the NPP part is completely handled by Sir, so I have no input there. But I'll also discuss like if there is something like that, I'll discuss with him and I'll also tell you there is something like that. But don't worry, NPP will be scoring. Like next NPP is going to be on probably on the language side. That is going to be easier to score. You get
இவன்
better
சத்தம்
score.
எதுவும் போடாது.
Okay.
Also, sir, I think like if I can just add,
Yeah.
I think there was a huge oversight in terms of because of NPP one, like Levin sir and your session both skipped week 6, like, and I
I got that because my week 6 session went into that NPP coding from scratch session, and then we had the quiz just after that. So we had to take the revision session for quiz.
and
It got
I felt like week 6 was the most had the most weightage for quiz 2
yeah,
is what
same
I
same yeah, same point. Yeah.
Yes, sir.
that was really
And
surprising.
week it also.
okay. See, actually, what I was
Sir,
told
please excuse
by
me.
sir that that
Sir,
week 6 has been covered in some session. So I thought it has been covered in the instructor session, but I think it got covered in the TA session probably. That's
It
what was meant by
it
it, and
got
that is why.
covered in the yeah, it got covered in the TA sessions, but like most people, like who I talked to, we were waiting for your or Levin sir's session that you'll cover week 6 because the YouTube lectures weren't really that great at covering everything.
Okay.
So we
So
were waiting for you.
do you want another session right now because week 6 will be in NTEM also. Like, do you want a session for week 6 or
I
is it
feel,
okay?
I mean, if you're asking for my opinion, I feel we should just continue with the week 9 or whatever right
No,
now.
that we will do, but separately. Do
After,
you want a session for
yeah,
week 6, like a 1 hour session on some
Yes,
other day?
sir. Yes, sir.
sure, yes.
Okay, what I'll do is then I'll just talk to the TAs. Maybe I can take one of their sessions or maybe one new one I can schedule and take it, not by interfering in their sessions. So next week, probably let's do it. 1 week, 6 session. Okay.
Okay, sir. Thank you.
Yeah, because I was also under the impression that it got covered in a session and our sessions went into the NPP. So that's why I think there was a miscommunication. But don't worry, we'll do it this time. And that is what I have also decided. Like this time also we have NPP, so my session I will be devoting it to the weeks only as usual, and Levin sir will take the NPP session, right? So that the week gets covered at least by one of
Okay,
us.
sir. Sir, Levin sir said that the MPP is, I think, around 12 of December.
Yeah. It's after 10th. Yes, around 12th. It will
Yes,
be
sir.
the week. Yeah, 12th is I think a weekend, right? So it will be something around that. Yes. It
Yes,
will
sir.
be kind of 1 week or 8-9 days before your end term. That week will be your NPP. Because actually before that the OPPs are happening, so we don't want it to clash with that. That is why we are shifting it by 1 week.
Yes, sir.
See, actually, the problem is after quiz 2 and before end term, the time frame is very less, and there are many exams like OPP, NPP projects are all clashing. So there will be some clash somewhere, but we are just trying to avoid that, and so that you can just space it out well from your side. Because as you said, tomorrow is the project, then next week onwards the OPPs begin. So that is why there are a few clashes that are going to happen.
So, sir, in NPP2, what would be like most important week for NPP2?
The
So week 8
RNN
to 10,
weeks, RNN and language, it will be like on based on that.
week 8 and week 7, like.
No, not seven. Yeah, seven, 7, 8, 9. Seven, eight,
Okay.
nine is important. Okay, it'll be on a like a machine translation on expert prediction, something like that. Sentiment. Okay, something.
Yeah, yeah.
It will be. It'll be
Okay.
easy, but sir has told me it
LSTM.
is going to be easier. Week the second NPP, because see, actually
Oh,
anything when you work with language, it is always easier than working with images because the code is also very straightforward, and generally any model you use it does a very good job nowadays to give scores even without good fine tuning. If you have done just a basic prompt based fine tuning, that also actually gives you a 90 plus score in many cases. So
um,
you're going to get a good
i-
score.
Sir,
in TDS
in
also we are using this LLM only, but that's not even understanding basic things. So that's why.
Yeah, but this will be easy. The NPP which is going to
Okay.
be set here, it's going to be on the easier side. So it'll be comfortable, more comfortable than the first.
Yeah, yeah. Last time also. Yeah.
Yeah,
sir
actually,
last
anytime when you work with images, it is always tougher than working with language. Language is always easier. Okay, so in most of the degree level courses, language comes first. Here, the image came first, so you got the tougher NPP in the beginning. This one is going to be easier on that
Okay.
side. Okay.
So please excuse me,
Yeah.
sir. I got uh, about the NPP, sir. In fact, actually, I had done both the models, that baseline and then rest
Fine
net,
tuning.
etc. But in
Okay.
fact, they have awarded 0 marks to that baseline model, sir.
Yeah. There are some issues with the marking. So what we will do is just have you filled the form, the discrepancy form which was released?
Yeah, in fact, I actually sent that form.
Yeah, so once you have filled the form, so don't worry about that. Next week onwards, we will the team, not me, Levin sir and the team who are handling the NPP, they will start resolving those issues and the updating of the marks will happen. Okay, because
The
this week
problem is,
actually
sir,
the
in
instructors
fact,
are busy with some vivas. That's why we could not do it this week. Next week it will be done.
okay.
Sir, just a general
Thank you,
question.
sir. Thank you.
Uh,
Yeah.
sir, yeah, as it's mentioned that 20% is for the model from scratch. Okay. So
Mm-hmm.
if the model is not from scratch, then is it possible to even score anything like to create these things?
Mm,
Not possible, right?
not sure. I think not. Yeah.
Yeah. So that doesn't make any sense. Model part from scratch, I got 0, like out of 20%. So I'm
No,
just
no, don't
checking.
worry. I will tell. So this time actually,
Yeah.
I think
Nee,
there are some
just
issues.
inform. Yeah, just asking normal question. I know you will tell this. Yeah.
Yeah, that is a good point actually.
Huh.
Yeah, we don't worry. On the
Yeah.
second NPP, you will find better rubrics for that. Yeah.
Sir, one more request. Last time for CNN, you covered a practical session, no? One session.
Yeah. For the
Like
NPP
that,
position.
if possible for RNN, can we have a
See, we can have, but the problem is week 6 got skipped because of that. So this time, one of the weeks will get skipped.
see,
And
we didn't see any simpler code. Whatever is there in the lecture collabs, that is only discussed. Easy collab, simpler, and very basic things we are not able to understand from there. That's why.
okay. I'll try. Let me see if I can have a session because see, I can take a session. That is not a problem. The problem is then one of the weeks gets skipped if we do a session for coding, right? Because see, actually, what happened was when we started the course, the thing distribution was Levin sir will mostly be handling the coding part, and I will be handling the theory, the normal weeks part. So if I go to the coding part, then it becomes coding, and then the theory session gets skipped. Of course, the TA session will happen, but since you were saying that you wanted my session for all the weeks, that is the issue then. that becomes a small problem. But maybe we can do that. Actually, the thing is that in the other courses that I'm handling, in that also the sessions clash. So that is why it is very difficult to schedule a off Saturday session. So let me see if something is possible. Maybe what I
So
can do is I'll cover a week 10 and
what
11
was the
in one session.
thing?
Yeah, yeah. Can you repeat?
Sir, what was the problem?
My voice is breaking. Okay. Is it fine now?
No, no,
No,
sir.
sir,
It's
it's
working fine.
fine.
Okay, okay. So the problem is that actually the other courses I'm handling, the sessions clash, right? So if I reschedule a session, extra session for some other day, it will clash with some other course. So that is the issue actually. That is why the sessions only happen on Saturday from my side. But I'll see if I can have another session for the coding and then continue the weeks. And now you want there is a week 6 session also, right? That we need. So some clashes will happen, but let me see if something can be scheduled.
Sometimes Livan sir is covering theory part also.
Oh, he's covering theory part also.
Yeah.
Like I feel for the second half for quiz 2 he covered all the theory for
Oh, is it?
like you
Okay, I
both
did not know that.
covering
I thought
theory.
he's only covering the coding part.
Pulkit, you yourself and Livan sir all are theory classes only. Only Punit is handling coding.
Coding. Yes.
Yeah, actually, there was a 50-50 division in the TAs and the instructor sessions. So, for one session for coding theory for TAs and one session for coding theory for us. So, okay, so I can cover the coding part. If sir is covering theory, I can cover the coding part of all the weeks. That is okay. But do you want, is it fine with you? Like, if I just cover the coding part,
No, sir.
you want me to cover the
If
theory
you
part?
cover theory also.
Yeah, I am also happier covering theory only, but it is okay. Let's see what can be done.
Oh, okay, then let's have only one small session for
That will do. Yeah, yeah. One session I will arrange. That is okay.
yeah.
Yes,
I
yes. I
feel
will do that.
as long as you and Levin sir communicate, like if one is taking theory, the other can take coding. Because some
Yes,
weeks
sir.
like both of
You
you will be
can take
taking theory.
the theory and Living sir take the coding part.
And then what if
I
sir
feel
says that I'll take the theory, you take the coding? Then what about that?
that's up to Levin sir then. We cannot do anything in that case. Huh?
See,
So
I
you
am actually okay covering both of them. See, the problem is in one session we can't cover both, right? That is pretty understandable. So that is why the division was happening. Now, since
Yes,
both of us are
yes.
covering theory, then we'll decide something. I'll talk to sir. Maybe I'll just tell sir that if possible, he takes the coding part and I'll take the theory part. If sir is okay with that, then it's fine. Like no issues from my side anyway. I am also okay with taking the coding part. But since you wanted me to also take the theory part, so there are a lot of needs and wants everywhere. You have to match them somehow and arrive at some optimal solution for this. But
okay,
anyways,
sir.
I'll take an extra session for coding. That I will do from my side. Okay, I think that will sort out the issues. Let the normal sessions go as it is, and I will take one extra session for covering the NPP2 part, like the basics of RNN coding. Right? That should be okay. That's fine, right?
Okay, sir.
Yeah, okay.
Okay, sir.
Okay, so yeah, let's start with week 9. Okay, week 9 is an easy week, so we don't need to spend much time, but it's important as well because it builds a base for week 10. Week 10 is the most important week of the course. 9 is the basics of that, and based on that, we'll see how we go to 10. Right? Okay, so 9 talks about again, we continue NLP, right? So if you remember, one second, something happened here. Yeah. Okay. So in week 8, if you remember, we started with NLP, which is natural language processing. And what we understood was this NLP will deal with models which will process text and give us output in text, right? So you have text here, you have a model which is there, and you get text. This is the cycle we studied. For this, we understood one class of models called as RNNs, right? This was the first class of models we have understood. Then in your week 8, you have seen some advanced models which are called as LSTMs and GRUs, right? So LSTMs and GRUs basically are just improvements on RNNs, which basically help the RNN to recover from problems like vanishing gradients, handling big sentences, and so on. Right? It's just the same architecture with some more weights and parameters that are added in the RNN. Okay. The third set of models is what we are going to see this week, and this set of models are called as encoder decoder models. Encoder decoder models are actually the foundations for modern LLMs also, like ChatGPT and all. They are based on a structure called as transformer, and transformer is arrived from this structure, which is called as encoder decoder. Okay. But before we move to encoder decoder, there is also one small topic that is covered that is called as word embeddings. So let's look at this first, and then we will look at encoder decoder after that. Okay, so this is the agenda for this week. So let's start off with word embeddings. One second, let me take a blank slide. Yeah. Okay, so word embeddings, we'll just take a small detour. Let's go back to our previous week 7. So if you remember, in week 7, we had discussed that whenever you pass text to a language model, the model cannot learn the text, right? Because model can't read a text. What model can read is only numbers. So the text that I have, this has to be converted into some numbers or basically some vectors, right? Some vector representation. And that vector representation we can actually give to our model, which will understand this vector representation and then basically do all the calculations and give me some output, right? So can you tell me the technique that we had used to convert text into vectors? What was the basic technique that we had used in week 7? It starts with O. That's
We're
right.
not encoding.
One hot encoding, right? So what happens in one hot encoding is, like, suppose let's take three words: apple, man, and woman. Okay, these are three words. So apple will become like this, man will become like this, and woman will become like this, right? This is what we have. Now, actually, if you see these one-hot encodings, these are fine, right? Because the text that I have been converted to numbers and I can actually feed them to the model. So it's fine. The cycle will work. But there are some issues that we had also discovered. So can you tell me what are the issues? If you remember from week 7, what are the basic issues with one-hot encoding?
So
Sparse
sparse.
vectors.
Yeah,
Sparse
sparse, right?
vector.
Because if you see, if there are 5,000 words, each array will have 5,000 numbers, out of which 4,999 will be 0 and only 1 will be 1, right? So we have too many zeros, which is basically causing a lot of sparsity, and that leads to memory issues, right? So we have issues in memory. That is one issue. Okay, let's ignore it for now. Let's assume we have a lot of memory and that is fine. The major issue that you see, which is in one-hot encoding, that is called as semantic issue. So what is semantic issue? Semantic issue simply means that words which are similar, the model should understand, right? Words which are similar, they should have similar encodings, and words which are different, they should have different encodings, because obviously then only the model understands language. I need to know that man and boy are similar, whereas man and woman are very different. Man and apple, they're absolutely different. One is a gender and one is a fruit, right? So that understanding should be there. So do you think that these vectors which you have, they are different? Here there is one is here one is here, and here one is here. All these vectors are different. But do you think that they are semantically also different, or do you think they are semantically similar only? What is the issue here? What do you think?
When we
There is
calculate the
no
distance between them, we get the same difference between all of
Exactly,
them.
right? So
So there's
basically,
no
a
difference.
measure of similarity is distance, right? If things are similar, then the distance is going to be small. If things are dissimilar, distance is going to be large. But if you see here, the distance between apple and man, that distance is going to be, let's assume it's x, right? It's root 2, but let's assume for now it's x. The distance between apple and woman will also be x, because if you see the magnitudes here, there is only one here, one here. So the distance, if you use any distance formula, it will come out to be the same value. And on the third side, if you see the distance between man and woman, this is also going to be x, right? Because again, one here and one here, so the distance calculation will give me the same value. So that means different words have the same distance, similar words also have the same distance. So my model is not able to distinguish between these words differently. It is not able to treat a fruit and a human in a different way. So is this good or is this bad? What do you think? It's bad, right? Because if my model does not understand the word groupings, how will the model do anything correctly, right? It's absolutely useless. So that is why whenever we are using one-hot encoding, the model actually does not understand the language very well, and it is not a very good approach to make the model understand or work with any language models, right? That's the problem. So basically, to solve this problem, we come up with a new approach, which is called as embedding approach. So what happens in embedding approach is very simple. You take a neural network, okay, and the weights that you see for the neural network, they are your word embeddings. Now, what do I mean by that? What I mean by that is very simple. Let's assume we have three words, okay? So we have three words, which are three neurons here. Then I take, for example, I take some hidden layer, maybe with 5 neurons. I'll tell you how this is decided. And I draw a simple network. So it will have weights like this, right? And so on. What do you think was the size of the weight matrix here? 3 cross 5,
5.
right?
3 cross 5.
So can I say that Can I say that these are my weights? Is it fine? 3 rows, five
Yes, sir.
columns. These are my weights, right? 3 rows and 5 columns. And do you think this looks like an embedding? If I see, it looks like an embedding. Like it just looks like this. It's an embedding. But now the difference is that instead of doing the one-hot encoding, I am making these embedding. Let's say this is apple here, this is man, and this is woman. So I have again learned the embeddings. But the difference is now that instead of doing a one-hot encoding or a predetermined way of encoding them, I have actually trained these embeddings using a network, right? A proper network which will have some loss function, some back propagation, some entropy, everything will be there. Okay. So what you will see here is now with training of the networks, the embeddings will actually have semantic meaning. That means the distance of apple and man will be much more than the distance of man and woman, because man and woman are humans, right? So the distance of these two words will be much lesser, whereas the distance of the embeddings of these two words is going to be much more. Similarly, the distance of the apple and woman, it's also going to be much more than the distance of man and woman. So the semantic meaning, the grouping of similar words, this will happen very well. But I'll tell you one thing. We have not done anything special. Instead of just initializing the embeddings with ones and zeros, we have now trained them in a neural network and got the weights. So how do you think doing that actually helps us achieve this? What is the reason behind it? Any idea?
Can you repeat, sir?
Yeah. So what I was saying is here we had a predetermined formula through which we did the embeddings, and we saw that this embedding method was very bad, right? Because the distances are all same. Here, what we did was we basically did not predetermine the embeddings with ones and zeros. We trained them with weights of a network, and obviously, you know that weights will be random values. So you'll get some values like this can be 0.7, 0.1, 0.3, some values like these you will get, which are the weights of a network, right? But we have just trained the network, right? So how do you think just by doing the embeddings in this weight training way, have we achieved this, which we require? How do you think it has happened? What is the reason behind it that this method actually works and this method fails?
Wait. Where?
But if you see, weights can be like this also, right? Like for example, man has 0.3, women has 0.9, 0.9, 0. Weights are random things, right? We cannot control the weights. So if I have this, if you see, man and woman are very different now. These are varied weights. Weights can be anything, right? But the distance between man and woman is very high. Then how am I able to say that this similarity issue, which was there in one-hot encoding, this actually got solved by this? How do we say that?
Optimizing.
Exactly. See, if you remember in your initial weeks, you have learned something called as this. Can somebody tell me what this is?
Gradient value
Universal
moment.
Universal approximation theorem.
Yeah.
What did the universal approximation theorem said? If you train a deep neural network with all optimizers, loss functions, and everything, you can achieve anything which you want. Right? That is a simple way of stating the universal approximation theorem. So the thing is that when you train the embeddings in a neural network, you are not going to just train it once, right? You're going to train it for epochs, multiple back propagations, loss functions, and so on, and you will keep training it until the loss function goes down, right? And once the loss function actually goes down, then this objective of making similar words similar and different words different, that gets achieved. Okay, so there is no mathematical reason behind it. The reason is simply universal approximation theorem, which says that whenever you take a deep network, that deep network makes sure that the embeddings are trained properly, and the semantic similarity which we wanted between similar words being similar, that gets achieved. So the weight values which you will see here, they're not going to be random. They will be designed in such a way that similar words will have similar weights and different words will have different weights. That we will make sure that actually happens. Okay.
So how will it happen? Like to optimize? I know we are optimizing things,
Keep
but
training. You will have some loss, right? So you will have some
mm,
loss, which is this. We'll not go into what the loss function is, but you
huh.
will have some loss function, which basically will be designed in a way that when the similar words are similar, loss function will be less, and when the similar words are different, loss function will be more, right? And you will keep training it till this loss function goes very low. And once this loss function is very low, that means you know that similar words have now got similar embeddings, right? So keep training it.
So how can that system get to know that these are similar? So we have to.
That is how the loss will be designed.
Okay, so a human will design the laws such that man and
Yes,
woman.
exactly. That is how the loss will be designed. It is actually, there are many variations of this. We'll not go into the mathematics, that will become complicated. It is called as semantic loss. Okay, so you can search about it.
Okay.
Semantic loss. So you design this loss in a way that similar words get similar embeddings and different words get different embeddings. Okay, and that is how the loss function will capture your essence. And when you keep training the network and minimize the loss, that means you're moving in the right direction. Just like any network, right?
Okay. Yeah. Okay.
Okay.
Yes, sir.
So the crux of it is, instead of using predetermined formula-based word embeddings, we have now gone into training the embeddings as a neural network, embedding network we call that. And this network basically helps the model assign the embeddings on the go by training weights and all, and make sure that we get good embeddings where we have this semantic similarity, right? So it is called this, remember this word, semantic similarity. This is what we wanted to achieve, and this is what we have achieved with this embedding approach. Okay. Now, one question that can come in your exams, like suppose, let's take a dummy question. So you have vocabulary, which is your number of words, right? We discussed this vocabulary word last week. So you have vocabulary which has, let's say, 10 words, right? And we create 50 dimensional embeddings. Let's call it E, right? So how many parameters are going to be there in this network? That's the question. Very simple actually it is, but this kind of question is quite important.
10 cross 50?
Yeah, exactly, right? Because the vocabulary is the words. So the words become your input, right? So this is your vocab. At the input layer, you have the vocabulary. And the 50-dimensional embedding simply means that each word has 50 numbers to represent it, right? Which is your hidden layers. That means there are 50 neurons here. So you have 50 here. So the network here will be simply 10 cross 50, which is going to be 500. And if you have bias here, you'll just add 50 bias, right, to it. So 550, so it becomes 550. This is with bias.
By
Are we
default, is
taking
there
buffer
any bias or
transport?
not?
Can you repeat?
Is there any bias by default, or do we just
By default, it's there, but in the question, if it's asked, it'll be mentioned what you have to find out, right? We'll mention that. So in case the bias is there, you just add the bias of the hidden layer, right? Because input has no bias as such, right? So we just add the 50 from the hidden layer. So this is
So
without bias.
in
Yeah.
real world, bias will always be there in real
Yeah,
world.
generally it is there. In real world, when we train a network, bias is by default there. Like we use PyTorch to train, right? So PyTorch includes bias by default in most of the networks. So it's going to be there.
Okay.
Okay, but for the exam point of view, it will be mentioned in the question, whatever you have to find. You can see in your assignments also, we have some questions on this. So you can see, like, if the question is just trainable weights, then only the weights you will mention. If it's mentioned that all parameters, then you will have to add bias as well, right? Same as before, what we did for the earlier weeks. Okay.
Okay, sir. Yeah.
So the dimensions of the weight vector should be 50 cross 10, right? Instead of 10 cross 50.
No, it is going to be 10 cross 50, right? Because it's going to be like this. For 10 words, like for example, apple is here. So you have a 50 dimensional embedding for apple. Then
50
mango,
features.
you have 50 here, like this, right? So 10 rows for 10 words and 50 is the columns, which is the number of embeddings for each word. Okay. So it's always going to be the vocab and the dimension, like this. Vocab cross the embedding dimension. Okay, because words are the rows, right? For each row is the word embedding. So that's why we'll take the vocab on the rows and we'll take the embedding size on the columns. Okay.
Sir, one confusion.
Yeah. What's the confusion?
So in week 7 and 8, we studied WHH, WIH, input. So we used to calculate like output into input, hidden
Yeah,
into input.
that is actually for RNN. This is an embedding vector. This is a different network. This is not the RNN. Okay, this is separate.
So sometimes we're confused, like how can we use that?
Yeah, got that. That was the convention for RNN. This is separate. This is for the encoder decoder model. This is a separate thing.
Okay, sir.
So for this one, you remember this one. For RNN one, whatever we discussed that day, I think I showed you the trick also, right, for the RNN. So that you remember for the RNN.
Okay, sir.
Yes, sir.
Yeah. Okay.
So
Don't worry about this. Actually, the dimensions and all is fine. Mostly the questions are on parameter calculation. So then the value will be same, right? Irrespective, because you just have to multiply. So it becomes the same thing. Okay.
We are taking X transpose then, right?
Yeah, this is a transpose. Correct. If the RNN is your X, then this is a transpose of it. But for right now, just remember that when you are treating the embeddings, your embedding words will come on the rows and the columns will be the dimension, embedding dimension, which is the 50 here, right? That will be the column because each row becomes an embedding. That's how you remember it. Okay, so I'll just write it also. Each row is a word embedding.
So it's always 1 cross something.
No, why is it 1? Yeah, 1 cross something. Yeah, correct. Each embedding is 1 cross something. Like suppose the embedding dimension is X, it is 1 cross X, right? Yeah. Okay, so that was the first part of week 11. So I hope that is comfortable. Any questions on this? Understood?
No, sir.
Okay.
Yes, sir.
Okay, so let's go into the next part. So next part is your encoder decoder model. So that we will discuss now. Okay. Now coming to encoder decoder models, this is a very simple thing actually. So what happens in encoder decoder models is pretty easy. So you have a model now. It is similar to RNN only. Okay, it's just like an RNN, but instead of having one stack of RNNs, you have two stacks. So one is an encoder RNN stack, and one is a decoder RNN stack. So basically, it looks like this. First, you have an encoder, which is a RNN, and then this encoder's final output. This gets fed into the decoder, which is also an RNN, right? So you have a decoder RNN here, and you have a encoder RNN here. So firstly, the encoder RNN will do something. Okay, some calculations, we'll see what it does. Then it will have some final output. So this is the final output here. And this final output gets fed into the decoder RNN, which again does something. And in the end, it gives you some Y hat, which is your last network output. This is the final output of the network, right? Which you see. Now, let me illustrate this with an example. That will be clear to you how it actually works. So basically, let's assume the task. What tasks are these models used for? So the most common task that these models are used for, so the task is translation. Okay, this is the most common task why such models were actually built. So for example, let us take a sentence like in English, I am a boy. This is a sentence and I will translate it into Hindi, right? Which is, suppose this is the translation. Ignore my spelling mistakes if any. So suppose this is the translation. Okay, this is what I want. So I have 4 words in English. I am a boy, and I have 3 words in Hindi. मैं लड़का हूँ. Right? This is what I want. So how will my model actually look like? So my encoder first will simply work with the input.
I'm sorry, sir. I think this is week 8. We have to see attention mechanism.
Yeah. I'm just explaining how this model works, and
Before
I'll
that,
come to attention
okay.
from this. Yeah. Okay, so just a recap first. I'm giving since week 8 also there were some questions, right? For this doubts were there, so I'm just giving a recap of this. Okay, so what will actually happen here is in the encoder decoder, very simple thing will happen. First, in your encoder, you will have an RNN which has multiple time steps, right? Each word becomes one time step. So this you have seen in RNN, simple, right? You have I here. The model will do some evaluation. This result will pass to the next time step, which will say am, right? This will do again pass to the next time step, which is going to say and this is going to pass to the last time step, which is going to say boy, right? This we know, the simple RNN, right? Where you have inputs of the previous layers going into the current layers and you have the current new inputs which get added up. Finally, this model, the encoder decoder model, will produce an output here. This output we'll see how it's produced. It's called as the context vector. So let me just write it by CV right now. Context vector. And this context vector is fed into the decoder. Okay. How does a decoder look like? Decoder is very simple. Again, just the same thing. Same steps will get repeated with the target. This one is for the input and this one is for the target. So that means again I'll have 3 time steps. First I'll give this word, then this will get fed to the next one where I'll give this word, and finally this will get fed to the next one and I will, no, not next one actually, that will be the last word, right? So we have 3 words only. So this one will give me my final output, that is this word, right? And now the translation is over, so we'll just stop here. So we'll have some token here called stop and we'll end the model straight away, right? So what I'm trying to say is here, very simple. Encoder will simply process the input like RNN. Step by step, it will do some calculations for the input. Finally, after processing all the input, it will store the information in something called as a context vector, right? And once it is ready with the context vector, in the end, this context vector is going to be passed to the decoder. Alongside the context vector, the decoder will work one by one by generating the target words one by one. So first it will generate the first target word, then it will generate the second target word, and then finally the last output will be the final target word. And once the translation from the source to target is completed, the model will stop there and then. That's the idea. So is the general flow clear how the translation system works for the
So,
encoder?
Yes, sir.
so decoder will translate
Decoder will translate. Encoder will take the input, decoder will translate.
and context vector.
Context vector is whatever the encoder has learned from the input. That is the context vector. Okay,
So
tell me one thing. Let me ask you a question, then it will be more clear.
Sir, I have a question.
Yeah.
Sir, can you just again come on the first and last tokens? So, for example, just at the last, you told that we don't need another recurrent block, and the last token in Hindi was the output, right?
Yes.
Now, let's go a little back. So, you said that the first token basically comes as an input, right?
Yes.
And for English sentence, boy
No,
was
first token
an
is not the
input.
input. The first token got generated initially, right? So that there's the first token with the context vector. It got generated the first
Okay.
token, then that went. It's not the input. So it is actually used
Okay.
generated from this, the context vector. It's not the input.
So can we say that in the decoder step, we had one less than the token?
No. Actually, that looks like it is one less, but it's actually not, because this step is also counted. This is also one step. So this is one step. This is second step. This is third step. The box is one less. See, if you want, you can represent it with the box as well. That is okay. But the idea is the first step is using the context vector. The first input is generated from the decoder. Then this is supplied to the next one to generate the next one and so on. Then the cycle continues. So this is also one step. You have to count this.
So
Okay.
is it
Okay.
true with I also? The I first one,
I gets counted. Yeah. I gets counted.
timestamp.
Yeah, counted. So see, time step is very simple. Just remember this. Whatever is the number of words in the source language will be the time steps of the encoder. Whatever is the number of words in the target language, that is the time steps of the decoder. Okay.
Okay. So
So this encoder will always have 4. This decoder will always have 3. In this case.
okay. So this English to Hindi translation, whose job is this? Like CV or context vector? Or
Yeah, that is what I'll tell now. So I'm just saying this flow is clear, right? How this flow is happening. Now let's try to understand each component separately. So if you see, firstly, the encoder. Let me see if I can take it to the next page, because the slide will become cluttered otherwise. Now let's try to understand what are the differences, okay? So difference is very simple. What you do in the encoder is, see, you want to translate. So if you want to translate the input is completely there with you, right? Or is it not there? What do you think?
input is there, no?
So suppose I say I want to translate this sentence, I am a boy. So you have the entire sentence with you, right? Which is I am a boy. We have the whole
Yeah.
sentence. There is no
Yeah.
lack of anything, right? But do we have the target? Anything of the target? We don't have, right? Because we want the machine to generate the target. We don't have any words of the target. We don't know the target language, right?
Yeah.
So input we completely have. That means this encoder, all the input time steps, they are supplied simultaneously. Okay, so you don't do one by one, because here I don't want to generate anything, right? I have the input completely. What will I generate? So all these I, am, and boy, these are supplied simultaneously. Okay. So all because I have everything, right? Generation will only happen when I don't have something. Like in RNNs, we saw a task called next word prediction, where using the previous words, we were generating a next word. Right? Why we were doing that? Because we did not have what the next word was. In case of encoder decoder, the input is already there with us, the source language. So there is nothing to be generated. So all these 4 words which are there, they are supplied simultaneously to the encoder. Whereas if you see in the decoder, do you think this is simultaneous or this is one by one?
Sequential.
One.
Sequential, right? For the decoder, it is sequential, because in the decoder, we don't have the target language. So first, what we want the decoder to do is, we have the encoder, this has the input. What we want is now, decoder will understand this input, and using this input, decoder will basically do, with this input, first it will generate the word, this one. Then with the input and this, it will generate the next word, which is this one. And then it is going to generate the last word, which is this one. Right? One by one. Because in the target, we have nothing, right? We are going to generate it one by one. It's a next word prediction kind of a thing. Right? So the decoder always works in a sequential manner. It sees the previous word, then it goes to the next word, then it goes to the next word, and then it goes to the next word. Whereas for the encoder, since all the input is available to us, we supply all the words simultaneously to the model, and the model processes them and gives an understanding. So what is the role of this context vector? This context vector is nothing. This is just an understanding of the input, which is given to the decoder. So understand the input. So what do I mean by this? Context vector is, see, if you want to translate an English word to English sentence to a Hindi sentence, you have to first understand, right? What is the English sentence? Because if you don't understand, how will you translate? So this understanding of the input is actually preserved in the context vector, which is given to the decoder. So this gives all the understanding to the decoder, and then with this understanding, one by one, the decoder starts generating the target language, and it completes the generation until and unless the thing is over, right? So whenever the final word is generated, then this information will stop. So this is the most important point. In encoder, everything is simultaneous, or basically it's in parallel, right? That's another word which we use. Whereas for decoder, there is nothing in parallel, because we don't have anything. We have to take previous word to generate the next word. So everything goes one by one. It is sequential, right? Stepwise. That is one important difference between the encoder stack and the decoder stack. So is
So
it clear
how
now?
So how context vector get to know like I have to convert from
That
this to
that
that?
we'll see that right now. In the next slide, we'll see that.
Okay.
Right now, just remember it is an understanding of the input. Okay, that's what you
Yeah.
remember for now.
Oh,
This is clear,
context
right? The flow.
vector, context vector is not the last time step, or is it?
No, it is not last time step. And context vector gets computed after. It is the last. It's not just for the last time step, but it gets computed in the end. That's why I've drawn it here. It takes into account all these things, but gets computed in the last time step so that it can be given to the decoder. We'll see how it works. Okay, but it gets computed in the end, but it covers up all the words. It sees and attends to all the words, and the attention mechanism which you were talking about, it actually uses attention mechanism, and based on that, it covers all the words together. But it gets computed in the end, and then it gets applied to the decoder in the beginning. After that, okay. So actually, context vector, if you see the drawing, will be like this. It covers up all the inputs, but the computation of the context vector happens in the end.
Sir, it should happen after the last time step, because the last time step also produces the output hidden state, right? So that is the
Yeah,
context
that is why it's
vector.
happening after the last, right? Once this boy is done, processing is done, then it gets computed after the last one.
Yeah.
At the end of the encoder. So just simply understand, at the last thing of the encoder stack is to compute this context vector. Okay. This last is just a diagrammatic explanation. It does not, because see, if I compute it here, then it will not be able to attend to this, this, and this, right? I need to make sure that it attends to all the words. So that is why we do it in the end, to show the process. Okay. You will understand it once we do the mathematical equation. It will be clear to you how this is actually working. But just to understand, it attends to all the words. It has to see the entire encoder stack.
Okay, sir.
I hope the flow is clear to you, right? Now, how the encoder is simultaneous and the decoder is sequential. Is that part clear? Any question on that?
Sir, is that for transformer based encoder decoder or something?
Transformer based is also similar. It has been derived from, this is the base encoder decoder. Transformer has improved on this. We'll see how the improvement actually happens, but it is a better version of this, more fast. It's a faster and improved version of this one. Okay. In week 10, we'll see that next week.
Okay, sir.
Yeah. Okay. Now let's try to understand how this context vector works. So just another quick recap. Let me draw maybe a smaller diagram in the next slide because it's actually too big. So suppose I have this again. So these 4 input words are there, which is I am a boy. And I've done the encoder. My encoder has processed all these 4 inputs, right? And now basically I want to supply this context vector into the decoder. So what I want now is the encoder has to understand the source language very well, right? So that only it can supply the context vector where the decoder will actually be able to predict the next target language, right? One by one. So what I want is at every step, let's say for the first step of my decoder, the word is "मैं." So what is this a translation of? Is it a translation of I am a boy? Which is a "मैं" is a translation of I, right? It's a translation of I. It's not a translation of boy, right? It's a translation of I. So I know that whenever I want to generate this word "मैं" here, I have to pay attention to the word I, because the I is corresponding to "मैं," right? No other word is corresponding to it. Then when I have the next word, which is this one, I need to know that I have to pay attention to this word, boy. Sequentially, if you see, I'll have to pay attention to this, right? One by one. It's not like that because the language constructs are very different for all the language, right? So for the second word of my target language, I have to actually pay attention to the 4th word of my source language. And when I have this last word, who, I have to pay attention to this word, right? Am. Okay. So that is the idea. So at every step of the decoder, for the generation to happen, I have to pay attention to different parts of the encoder, right? Because the way the source language and target language is constructed is very different. So it's not that for the first word I have to pay attention to first word, second word to second word. It's not like that, right? Because if I do like that, this will become "मैं हूँ लड़का." That is not what we want, right? We want the accurate prediction, right? So that is why this idea of attention mechanism actually comes from here. That basically what we do is we instruct the model to pay attention to certain words, okay, at a particular time step than some other word, so that the model correctly understands the correspondence. Like this word of English translates to this word of Hindi. This word of English translates to this word of French. So we want this understanding of the model to be very accurate. You pay attention to the correct word rather than paying attention to the wrong word. That is what we want. Okay. For every word, it's different. For the first word, the attention was here. For the second word, the attention was here. For the third word, the attention was, let's say, here, right? So for every word, I want the attention to some other different word in some other order for the source language. This mechanism is called as attention mechanism, and this processing is actually done using this context vector. So here come the context vector comes into use.
So just a quick question.
Yeah.
Like we chat with a ChatGPT.
Yes.
Okay. So it can either generate a pure Hindi, or it can also generate a Hindi which we speak.
Yes. Correct.
So like how it gets to know, or it's trained on those data. That's why it
It is
gets.
trained on those data. Yeah, it is
Oh.
trained. Anything which it generates, it has to be trained on something on that sort. Okay.
Oh.
Yeah. So is the idea clear? Like, why do we need attention mechanisms? So that we can actually focus on the relevant part of the input rather than doing some haphazard computations. That is the idea. That why we need attention mechanism. Is that clear to everyone?
Yes, sir.
Okay. Okay. Now let's try to understand how this attention mechanism is actually done. So for that, if you remember, there are some equations given in your week 9 as well. So some way to compute these weights. So those equations, again, for the exam point of view, you'll have those equations. You'll not be asked too many heavy computations on that. So it is a mathematical formulation through which we compute the attention weights. But let's first try to understand what these attention weights mean. Okay, so let's come to attention weights. Attention weights are actually computed for every word of the decoder. Okay, so suppose I have 3 words in the decoder. For every word, separate attention weights are computed. Because obviously the reason is very clear. Okay, can you tell me the reason? Why do we need separate attention weights for every layer, every word? Can you think of a reason for that?
So let's suppose we have this last word of Hindi,
Hmm.
so which is not matching with.
No, say for example, I say that my model has attention weights. Since there are 4 words, so I'll get 4 attention weights: 0.4, 0.1, 0.1, and 0. Let's say 4. Or let's make it a little different: 0.6, 0.1, 0.1, 0.2. That means most of the attention will go to this word I. Very few attention will go to these 2 words, and little attention will go to this word. So can this logic be correct for all these 3 words? Can we use these weights for all these 3 to get accurate
Every
translation?
word needs different attention for each of them.
Exactly. So for each word of the decoder, I need separate attention weights, right? Because to make it focus on the correct word. That means this one, this layer of weights which you see, this is very good for this first one because man is paying most attention to I. So this is fine. When I come to this word of the decoder, that is ladka, so I need the weight something like this, right? 0.1, 0.1, 0.1, 0.7. This is correct, right? Because this is paying most attention to the word boy. Correct. And when I come to the last one, so when I come to the attention for this, I'll want 0.1, 0.9, 0, something like this, right? Where I have the correct mapping. So because every word of the decoder corresponds to different words of the encoder, one set of attention weights for all the words will not work because that does not do anything, which is correct, right? So that's better is not to use it only in that case. So to make sure that the attention mechanism works correctly, for every time step of the decoder, we need separate attention weights, right? So for all the weights, we need some attention matrix, attention weights, which will basically correspond to those words correctly. So for the first word, we need the weight so that we get the correct one, the maximum weight. For the second word, again, we'll need it somewhere so that we can get the maximum weight to the correct one. Right? That's the idea. That is why for every word of the decoder, we need separate attention weights. So obviously because of that, and we have a structure called as the attention matrix, right? And this attention matrix will basically help the decoder to tend into different parts of the encoder. So can you tell me what is the shape of this attention matrix? What do you think? Like based on this logic, can you tell me what is the shape of the attention matrix?
Like 3.
Yeah, for this case only.
3 cross 4?
3 cross 4, right? 3 cross 4. And if you see, it's going to be like this. So this one will tell me for me which words I have to attend to. This one will tell me for ladka which weights I will attend to. And this one will tell me for this word who which weights I will attend to. And these will be I am a boy. And we know that for the first one, I should pay most attention to this one. For the second one, I should pay most attention to this one. And for the third one, I need to pay most attention to this one. Right? And rest of it will be, it's a probability distribution. So the sum will be 1. So it's going to be something like this, right? So that is why for every word of the decoder, I will pay attention. I will pay attention to everything because I need to know it's a sentence, right? So I have to pay attention, some attention to everything. But I will make sure that the attention is proper. How is attention proper? Where I pay most attention to the word that is relevant and when I pay least attention to the word that is not relevant. That is the idea. Okay. So that is why for every encoder decoder stack, we have an attention matrix. And this attention matrix covers the attention weights for all the time steps. Okay. And the shape generally is the decoder time steps cross the encoder time step. Okay, because decoder will give me all the decoder words and encoder time steps will give me all the words I have to attend to. And I will basically design a distribution through which I will maximize the correct attention. Okay, so maximize correct word attention. Okay, so that is the idea. So is the idea clear, like how the attention matrix is formed and what type of results are we expecting from the attention matrix? Are we comfortable with that?
Yes, sir.
Okay, so that is good. Okay, now tell me one more thing. Attention matrix, we need to make sure that it pays correct attention to the correct word, right? So how do you think I get this attention matrix? How do I get these weights? What is the easy way to get these weights? Do I do
Just
some probability distribution? Do I do some formula or do I do some training? What is the best way?
training based on weights and all.
Exactly, right? Because just like the embeddings, right? That is why word embeddings come to relevance here. When you wanted the correct embeddings, you just set an objective on the neural network and you train the network and you got good embeddings, right? In the same way, the attention weight, there is no fixed formula because for every word, the attention order will be different, right? So you can't actually use a fixed formula and do attention like that. That is not possible. So that is why for every way of going into these attentions, we need to make sure that we do the attention training very well, and all these weights we update through some matrices, right? So we have to take some weight matrices, we have to design some neural network, and based on that we do the attention mechanism, right? So that is why this attention weights, they are trained. Okay, so that is why you have some matrices, weight matrices, and based on those weight matrices you actually train these attention weights, and with the attention weights you are able to finally do the computations. Okay, that is why this is actually quite a relevant question, at how do you obtain attention weight? Do you hard code them? Do you have a deterministic way or do you train them? You have to train them because for every word the attention order becomes different, and that is why to make sure that the attention is working in the correct way, we have to make sure that the attention weights are trained. We cannot actually go about working with random initializations. We have to train them properly so that the semantic relevance again makes sense. That's the idea. Okay. Okay, so any
Yes, sir.
questions so far? Any doubt? Okay, that is great. So now that we have understood the attention matrix, let's try to understand how this context vector is formed, right? So if you see, let me again draw the diagram so that it makes a little sense of how it is working. So I have this and we have this here. Let's come to the first word only right now. So here I want some context vector, and I told you that the context vector will basically give me the representation from the input. So basically what happens is this word "मैं" should get an idea that I have to take care of 4 inputs, and these 4 inputs I have to give maximum weightage to the word "I." Right? For that I already have an attention weight. Attention weights are denoted by alphas. Okay, that is the notation that we use. So we have some attention weights that are also available. So how do I think? How do you think I give an compressed information to this decoder? What is the way of doing it? We have alpha 1, we have alpha 2, we have alpha 3, we have alpha 4, the attention weights. For this time step of may, we have the 4 words of the encoder. So how do you think we supply the information to the decoder?
Hidden states or
Yeah, hidden
like
state also we have. So we will have some H1, some H2, some H3 and some H4. So now with these 4 alphas and 4 hidden states, how do you think the information will get conveyed to the decoder?
multiply them in summation.
You can simply take a linear combination, right? Multiplication and summation. So if I do alpha 1 H1 plus alpha 2 H2 plus alpha 3 H3 plus alpha 4 H4, this becomes your context vector and this goes into the decoder. And what you see actually here is the attention idea is also captured because the maximum relevance will come to the first hidden state because the alpha 1 is the highest, right? So the first hidden state gets the maximum say in this vector. And all the ones which have lower attention, they will all have a very small say. So the magnitude of this context vector will completely depend on the highest alpha. So that is why this captures attention very well. Let me repeat this again. So basically what we want is at every step, we have attention weights. At every step, we have hidden steps because it's an RNN only in the end, right? So you have hidden states at every step. And we have to make sure that we supply this attention information to our decoder properly. Where we need to make sure that the word which has the maximum attention weight, it gets the most value, and the word which has the least attention weight, it gets the least value. So how do you get it? You get it through something called as a context vector. And what the context vector simply does is it just computes a linear combination of the attention weights and the hidden states. So alpha 1 H1 plus alpha 2 H2, alpha 3 H3, and alpha 4 H4. How does this solve our attention problem? Because alpha 1 is the highest, so whatever magnitude of H1 is there in this whole sum, H1 will dominate that sum, right? Because the other alphas are very small, the way of the values of H2, H3, and H4, which will come to the context vector, will be very less. So this will be dominant, right? The correct word in the attention mechanism will contain and retain the dominance, and all the words which are not relevant will not have any dominance in that particular sense. That is the idea, right? Similarly, when I go to the next step now, which will be your this one, the second word, I'll have some separate alphas for it, right? So let's call it alpha I J K L. So in that one, I'll have alpha I H1 plus alpha J H2 plus alpha K H3 plus alpha L H4, right? This is for the next word. So for the next word, we have again separate attention weights, right? So now we'll take these attention weights and we'll get the next context vector, which is context vector 2 for the second word. And that we will supply to the decoder. And if you see for context vector 2, this word had the highest attention weight, right? So that is why this will dominate in that case, right? It will have a knowledge of all the words, it will have the knowledge of the entire sentence, but the dominance will come from the correct word where the attention has to be paid to.
Sir, I have a
Uh,
question.
Yeah.
Sir, sir, I have a question. I don't know if like it's like correct way of asking, but in RNN we saw that when hidden states were passed from one step to another, we were using non-linear functions to pass that information. But now we are using a linear combination to create a context vector.
Yeah,
So,
right.
so why are we going back?
Uh, so in RNN, the thing was you were using tan H, right, to give the contribution, because in RNN, the objective was next word prediction. So tan H and sigmoid, these were giving you probabilities of what the next word is going to be, right? Like for example, in RNN, we had something like this, right? So you complete the sentence, I am a, and it will know the next word is boy. So with the help of sigmoid or tan H, it was basically giving you probabilities. And then you were scaling the hidden state by that probability. Right now, we don't want anything to be probabilistic, right? What we want is this context vector will just tell the decoder that which word is important from the encoder. So that is why we have 4 hidden state representations for the 4 words, and the attention weights are telling you which word to pay more attention to. So that is why whichever has a higher weight, that will dominate the sum. So our objective is different. It's not that we are doing something differently. Our objective is now completely different. In RNN, the objective was predict the next word, right? Here, the objective of context vector is give importance to which word of the encoder for the next word of the decoder. I'm not predicting the next word here like this. I'm just saying that for this particular word of the decoder, where do I pay attention to? Which word do I focus on from the encoder? That is the problem, right? So the objective, the way of designing the model has changed now.
Sir, that is right, but let's say that non-linearity was different. Then we, when we are optimizing that in backprop also, those derivatives very different. But here, like it's a linear combination. So don't you think there can be other aspects which can be limitation of this linear
No.
combination?
See, actually, the thing again is the same thing, only about the objective. We are not going to backpropagate the encoder and the decoder together. Encoder will get backpropagated separately, and you'll have non like here some sigmoid or tan will be there to predict these hidden states. I am not actually doing anything with the encoder right now. What I'm doing is I'm taking each step of the encoder and giving some representation of it to the decoder. In the RNN, what we were doing was we were just predicting at every step what is the next word, right? So for that, we had those non-linearities which were helping us doing the prediction, just like a normal neural network does. Here, I'm not doing any prediction right now for this context vector. What is context vector doing? It is just taking a representation of the already designed encoder and giving it to the decoder. It's linking two RNNs basically. This part is not any prediction part. It is linking of two RNNs, the encoder RNN and the decoder RNN. So I'm supplying some information of the encoder RNN to get it to the decoder RNN. I'm not going to backpropagate on this. This is just the attention, like which parts
Okay.
of the encoder are relevant to the decoder. Okay, within the encoder and decoder, I already have those RNN formulas working out, right? That is already there. So there I will
Sir,
backpropagate. There I'll have the sigmoid and tan H. This is just showing whatever from this is relevant to this. Okay, no
sir,
predictions
but
will happen.
these alphas are learnable, right? That's what.
Alphas are learnable, but we don't backpropagate the network for alphas. We backpropagate the alpha network. That is separate. So how you learn the alphas? You have two additional matrices that learn the alphas. That is not a part of the network. So that we backpropagate separately with the objective of for giving representations. Okay, it is not a part of the network that is there.
Sir.
Yeah.
Did not understand.
Yeah. So you said that Hindi translation is मैं लड़का हूँ. Okay.
Yeah.
So in the last word who, so that is not matching with I am a boy in any of the words. So how even if you give weights to am the more for the third one, how it's gonna like translate like?
No, who is a translation for am, right? I am a boy, so मैं लड़का who means am. That is a correspondence to am, right? It
But
is not
how
a
can
word
you
to word translation, but the
get to,
focus should be on am, right?
yeah? So it cannot translate to who, right?
No, it will, right? So if you do I am a boy, मैं लड़का who is the translation. So the am goes into who, right? That is how it works.
But it cannot translate to that exact. See, I means मैं. That's very clear, right?
Right. Boy
And
is लड़का. That is also
yeah,
straightforward.
but the last one is like that's not corresponding to am or a, both of these. So even giving weights like does that make any sense? Because that's not translating to that Hindi word, that exact.
See, Acha, you are asking the translation of the word am is not who. Is that what you're asking?
Yeah, I can be translated to मैं, okay, because I has been given the maximum weight. Then comes boy, right? But for whom we are giving maximum weight to am, right? But
Hmm.
am, how, what's the significance of giving this much of weight to am when we know that am is not equal to whom?
Am is equal to who? Try on your Google Translate. You write I am, that the translation comes out to be मैं हूँ. It is equal
Okay,
to who.
okay, let's suppose we have some another word, so
Okay,
that
so now suppose we have some word which does not translate to anything, right?
yeah,
So in that case, what you do is you have to attend, but what you don't have the attention weights which are there, those won't look like biased to some word. It will look uniform to all the words in that case. So when there is no direct translation, the attention will look something like this: 0.25, 0.25, 0.25, 0.25. I have to attend because I have to get some information from the encoder to the decoder, but I will not like design the weights in such a way that you get information, the attention, especially for one word, but you basically attend basic small attentions to all the words in that case. Uniform attention, no biased attention. Okay.
so in that case it has to take all the sentence and it has to translate as per the training, like
Yes, based on the training, whatever it has learned, it will take something from its vocabulary or tokens from the vocabulary and do the translation based on that.
whole sentence.
All
Okay,
sentence.
okay.
Yes. See, that is why training with large data is important, right? Because if you don't train with large data, the model will not understand many things and the translations will become haphazard. That's why train it
Mm.
with multiple words so that the model understands relation between all sorts of words and gives you the most accurate result. For language
Yes,
modeling, the only thing that has to be concerned is, see, if you see all the GPTs, evolution of all the language models, the main thing that has changed is the data set size. It has kept on increasing. And once you have kept on increasing data, you have kept on making it more diverse from different sources, the accuracy of the model has gone up every time. Okay, so it's
yes.
like that. Okay, so that is the thing. Yeah, any other questions from this so far? I hope the context vector and the attention weight part is clear, right? That is very important actually. If you have any doubt, I can repeat it again if you require. Okay, so I think it's clear.
Sir, could you please repeat the dominant part? What you said about that?
Yeah. So what I was saying is at every where the context vector is getting generated, you are basically taking a combination of all the words, right, with the attention weights. So obviously we need to know that in this combination, the maximum value should come from that word, which is the correct word, right? So for this word "मैं," the correct word to attend to was this word "I," right? So that is why we know that the alpha one will be highest for "I." That we saw here, right? This value will be highest for "I." And when you take this sum, and if when you do alpha one H1, alpha 1 is very high, so the h1 value which goes on to the sum is going to be very high, right? Whereas here the alphas will become 0.1, 0.1 and so on. So the values that of h2, h3, h4 that go will be very less. So the maximum value that's going to be there in the context vector will come from h1, which is the correct word, right? That is the idea of dominance. So with the attention weight, you scale the hidden states and the words of all the sizes, and the maximum value comes from that word which is correct. Okay.
Okay, sir.
Yeah, so that is the main thing. Like this is a basic logical idea that the word that I want to attend to, that will have the highest weightage amongst all the other words.
Okay, sir.
Yeah. Okay. Any other questions from this? Anything which is not clear?
Context vector 1 and 2 are different or
Yeah,
same?
yeah, yeah. For every time step, you have to supply a context vector.
The same context vector will be supplied every time.
Not the same one because the weights change, right? So different vector at every time. The hidden state remains the same, but the weights will change at every time step. Because
Okay.
the weights for "मैं" will be highest for this word "I," right? Whereas weights for "ladka" will be highest for this word "boy." So the weights keep changing, right? That's why we have different context vectors given to each time step. The way you compute it is the same, but it's just the weights which are coming out that is different.
Initially, we used to say that context vector as a simple vector from encoder input, no?
Yeah, basically the idea is context vector is summarizing the encoder for the decoder, right? And that is happening at every time step of the decoder. Some different summary is going on. For the first time step, the summary is going on with importance to the first word. Second time step, the summary is going on with the importance to the third word, and so on. So it's just summarizing the encoder, like it's taking up all the words, but it is giving importances at a different scale. Whichever word is more relevant, that is getting more importance. Whichever word is less relevant, that is getting less importance. That is how it is scaling it up.
From May to Ladaka, which vector is going inside for?
For May to Ladka, so for May the first vector is going, which is with the words of the weights of May, right? So this vector is going, this vector multiplied by the hidden state. For the Ladka, these weights are getting multiplied with the hidden state. Hidden states are same, it's just that the weights are changing with each word.
Okay.
Okay, because hidden states are already represented, right? So that those won't be different, those are same always. But in the end, the weights which are there, they are changing for each time step.
Okay.
Yeah, so that is the thing. Any other question?
No, sir.
Okay. So yeah, so that is basically the idea. Then we have implementation of machine translation. That too is the coding part. So that is okay. One more thing that is quite important for this week is how you actually get these weights, right? So there are actually two ways. We will cover it in more detail in the next week because it's actually the way that they have described here in this week. It is the transformer way. Since transformer is going to be computed next week, we will cover that in next week. But I'll just quickly give you an idea of how it is done. So the attention weights are computed with a formula, and that formula is called as Q K transpose V transpose, sorry, V divided by root D, and you do a softmax here. It looks very scary for the beginning, but I'll just tell you what this is. We will discuss this in the next week, okay? Because this is more relevant to transformers. That is where this got invented. In traditional encoder decoders, this was not there. So how it's done actually is Q is one matrix which is done. So if you remember, I told you these weights are trained, right? So that the maximum accuracy can come, semantic accuracy. So we have Q, which is one matrix. We have K, which is one matrix. This is a separate matrix that is there. So two matrices, and you have to train them, right? So this you train, this you train. Actually, sorry, there's one small mistake here. This is not there. Only this much is the formula. Then this D is basically the dimension, right? So the size, the vocab size. So this vocab dimension is there in D. Okay, and here you have a final softmax that basically multiplies all this and gets you. So basically what is happening here is there is one matrix here which is a Q matrix. There is one matrix here which is a K matrix, right? Q matrix corresponds to the decoder. So this comes from the decoder side. K matrix corresponds to the encoder. Okay, so this comes from the encoder side. So that, see, decoder side means these words, right? These words will correspond to the K matrix. Encoder means these words will correspond to the Q matrix. Okay, then you take some representation of this and you multiply them. Once you multiply, you get a square matrix as an output. Again, this is going to be discussed in the next week, so I'm just giving you a teaser of how it's done. Once you get the output, you have these attention weights that you wanted. All these attention weights are ready. And in the end, we do something called a softmax, right? Softmax, you have already seen what it does. So what does softmax do? What is the use of softmax here?
Normalize.
Normalize, right? Because we want probabilities, right? So this will give you a normalization. So like this 0.9, 0.8, 0.1, this normalization. That's why we do softmax. Because when you multiply word representations of Q and K, you don't get values between 0 and 1. But since we want to normalize it and give a probability hint of the encoder, of the attention, so we use a softmax to normalize it in the end.
So isn't the total probability be equals 1 in
Yeah,
softmax?
sum is 1. Sum is 1. So suppose this is 0.9, this is, let's say, 0.05, this is 0.05, this is 0. It's always going to be sum is equal to 1. Okay.
Oh.
Yeah, it's a row wise softmax. So just remember it as a row wise softmax. Okay, because row is for each word, right? And I want to see the attention of each word of the decoder to all the words of the encoder. So we do the softmax row wise for that case. Okay. So this is how it's done. So basically the objective of this was that encoder and decoder, both of them, they will give you two new matrices. One is the Q matrix, one is the K matrix. Okay, K comes from the encoder and Q comes from the decoder. And with these two new matrices, we do some combination of it and we train the attention weights. That is the idea. That is how we can say the attention weights are trained, right? And in the final, we do a softmax. The role of the softmax is very simple. You want the weights to be probabilities to give the highest probability the maximum attention. So that's why we apply a softmax and just scale them up. That's the idea. Okay, this we will discuss in the next week. How this Q matrix comes, what is the dimension of this Q, what is this K, what is the dimension, what is this D, what is how the softmax is applied. We will discuss in the next week. This was just to show you that attention weights are obtained by training. Okay, that is why we get good weights. So how do we make sure that we have actually good weights where the correct word gets the most attention? That is because we train it. And again, the universal approximation theorem comes into play, right? When you train anything, you get the correct objective. That's the idea. Okay. So for now, you
Sir,
can ignore this for now. Just remember that it's trained and two matrices are there. The idea and the dimensions of all this we will take up in the next week in detail. This was introduced in the transformer. Okay, so transformer brought this idea.
Sir,
sir,
though I
week 9 is
understand.
this much only.
Yeah, so the sir has covered up a little bit on QK and the D, this formula, but this formula for now you can not take it up much seriously. I'll cover it in more detail in week 10 because week 10 is where transformers are introduced and this is used in transformers. Okay, so I'll explain it in week 10 in more detail. Otherwise, content wise, this much is what is important for week 9.
Sir, with transformer you mean LLMs like?
Yeah. Transformer is LLM. Yes.
Okay, sir.
Sir, yesterday with Livin sir also we told to share some material which where we can understand this a bit more better for
Which
week
part?
8. Yeah.
This Q
So
and K, this one.
yes, sir. How sir has covered right the entire piece. Just to understand that better, if you have some resources around this
I
topic,
have some good slides from the DL course. It's not like my slides, the DL slides. I can share that with you if you require.
y- yeah, which is like every step is explained clearly, right? It doesn't leave any ambiguity. That will be
Those
helpful.
slides are very good. I will share it with you on Discourse after this session. Okay, because I have to find them. It's there with me. I have to find it. I'll just upload it to my Google Drive and share you the link of the slides. But don't
Yes,
worry
sir.
about it. I will explain it in step-by-step detail in the next week. I'm not doing it this week because this is a transformer topic, and right now we have not understood what transformer is. Before that, we have to understand how a transformer works, and then this will be clear. If you don't know what a transformer is, then explaining this becomes slightly hard because this is based on the architecture of a transformer. Okay, this is actually very simple. There are 5 steps which are used to compute this entire thing. I will explain you all the steps one by one in the next week session. It will be clear. Okay, don't worry about that. I will make sure it is clear.
Yes, sir. The content on D2L and that both the references also is not that easy to understand. So we
Don't
need
worry.
some easily
Just you
understandable.
attend the next Saturday session. We will take it up completely, slowly, step by step, and it will be clear for sure. I can guarantee you that. Okay.
Yeah,
The reason
sure,
I'm
sir.
not doing it today is because if I do it today, then without knowing the transformer architecture, this won't be clear. You won't understand how it works. It'll just be like memorizing the steps. Next week, once you understand the transformer architecture, this will be very clear of how it actually works. Okay, because see, there is actually a small mismatch in the lectures. This has been covered in the encoder decoder, but this is not actually how encoder decoder attentions are computed. That uses a very different approach. This is actually a transformer attention, and they have covered it here in encoder decoder. But without understanding transformer, this will be very hard to comprehend this. So actually, this is a week 10 content. You can think of it. Week 9 you can cover till here. This will be clear. This is all you have covered in week 9. This is something we will look in more detail in week 10, because on week 10 this will be very clear once you understand transformer.
Okay, sir.
Yeah. So I hope the idea of attention weights, context vector, step-by-step computing of the encoder and decoder, at least that much should be clear, right? Machine
Yes, sir.
translation, how it works. Yeah. So that is good. Hmm. Okay, one more thing, one small question. So in encoder, if you remember, all the words are available, right, in the beginning. Whereas in decoder, the words are coming up one by one. So how does the word come? Like, what do you have in the end to get the correct word? It's an RNN, right? So what do we have in the top of the RNN?
Hidden
What's the next word?
output.
Output layer, right? A softmax, basically. A softmax over the vocabulary, if you remember, right? In RNN, in the end, we had a softmax over the vocabulary, right? To show which word from the entire vocabulary is the most probable next word. So that is still there. So I'm just trying to say that encoder decoder, the architecture is nothing but two RNNs which are squished with each other, right? The only addition that is there is this context vector. Rest everything, how the internal thing of the encoder is working, how the internal thing of the decoder is working, that is same. There is no difference in them, right? You have the softmax, you have the hidden layer, the embedding layer, everything is same. Okay. So it's just that two RNNs are there, independent RNNs, and I have squished them and connected them with a pipe, which is the context vector. So think of it like that. So all the architectures of the RNN, all the parameters of the RNN, everything is there. The only additional thing that has been added is the context vector. that I'm supplying with the attention weights. The rest, everything remains the same. Softmax in the end, the hidden step, the hidden matrix, everything is still the same. No change. Okay.
Sir, we talk about like vector embeddings in LangChain and all. We are
Yeah.
working with PDF and also these are the same only.
That is slightly different. It is kind of the same. It's just that in that what you do is for every document you generate an embedding. Here what you're doing is for every word you're generating. So that is more like a multi-level word embedding kind of a thing.
Okay, sir.
Okay, but the idea is same. Yes, same idea.
Okay, sir.
See what happens. Like for example, when you're using lang chains, you want like for example, you uploaded a PDF about your curriculum, right? And then you ask the question. Like two PDFs are available. Like one PDF says about data science, one PDF says about programming, right?
Mhm.
So you ask a question on data science. That question will be first converted to an embedding, right, for the model, and you want that embedding to be matched to the embedding of the data science PDF, right? And then you match it and retrieve it from there. Whereas the embedding for the programming PDF will be very different, right? Because that is not data science. That's very separate, right? So that will
So,
be a different embedding. That's what we're doing at a high level. Okay.
okay.
So here we
Uh,
are doing word wise, there we will do document wise.
okay, sir. Just asking, like I haven't found any true program. Maybe you know that something like Chat PDF. So have you ever worked or have you ever find something called Chat PDF where you can upload a PDF and you can chat? Like, is there a system available? Or
I
because
have
I'm
built a similar thing like for one of my projects where basically you upload PDFs and then you can just ask questions there and it will retrieve the information from the PDFs and give you.
is it working successfully, sir?
Yeah, it is working successfully. It is called as the PDF is called as a knowledge base and the system is called as a, have you heard about RAG? RAG,
Yes,
it is
sir.
a RAG system, right?
Yeah.
So I've built RAG pipelines and it is very, actually it's very easy to build. With LangChain only I have built that. So first you have to create the data vector database for it, which is the embedding database using the PDF, and then basically you do the matching with distances or cosine similarity, and then you retrieve the information from there. It is quite a simple system, and yeah, it's working. I can
Yeah.
show it to you next week in the session, and we can see how it
Sure.
works. Yeah,
Sure,
yeah.
sir. Love to see that.
Sure, we'll do that. Next week I'll show it to you.
Yeah.
RAG is actually very fun to work with. When you learn RAG, it is very good. It
Sir,
is very
very
helpful.
interesting, sir.
Yeah, very interesting. Absolutely. We'll see RAG, okay, a little bit. We'll not do RAG much in this course, but a little bit of it we will see in the next week as well. So I'll explain you like in basic how it works next week.
Yeah, okay, sir.
Okay, so that is it from my side for this week. If you have any other question or any doubt and anything, we can discuss. Otherwise, we can wrap up after that. Any questions?
Sir, regarding week 9 and 10 content, when I saw the Transformers architecture, I'm confused whether are we supposed to remember the exact Transformers architecture or something similar to that for end-term preparation? Because
The
that is very
architecture, like
complicated.
the week 10, the transformer architecture, you have to remember. Yeah.
The entire architecture, like
It is,
positional encoding, multi-mask attention,
yeah.
everything.
You have to remember that. Yes.
That's so complicated.
It won't be. You attend the next session, it would be easy. Okay, don't worry.
Okay, sir.
Yeah, I'll
We'll
send.
prepare it in advance. That would be better.
Can you repeat once again? Voice was break. Can you repeat?
Yeah, week 10 we'll prepare in advance. That will be better, right?
Yeah. Week 10, I will take a longer session for that. Week 9 was quite simple. Week 10 is the
Mhm.
main week actually because it summarizes transformer. We will study the entire transformer in detail and I will show you with a
Mhm.
practical example of how a transformer works step by step. That will make it clear.
Okay,
You don't
so
have to memorize. Once you understand the working, it will be very clear how the architecture works. Right?
okay,
It
so
is
if I
very
if I refer lecture videos, and should I watch like this week 9 or directly from week 10 I can start
for
right now?
transformer. See,
Right
week
now.
9, if you have understood whatever we did today, then you can start with week 10 straight away.
Oh, okay, that's great. I understand 100% everything. Yeah.
Then it's comfortable. That is mostly this is all in week 10. In week 9, sir has also explained that QK matrices, but that we will do in week 10 because then it will be more clear in week
Okay.
10. Okay. For now,
Okay.
just remember that there are matrices through which you train the attention weights. They are trainable, right? That's what you need to remember for now.
Got it.
For
Thank you.
transformer, and don't worry about anything. Just attend next week's session. It will be very clear how transformer works. Okay, that I can promise from my side. Right now, you can watch the lectures to get an idea and practice the questions as well as much as you can. Then next week we will make sure it gets cleared for everyone, right?
Oh,
Yeah. So week 11 also is based on week 10. So actually, both the weeks can be very easily tackled with that architecture. But yeah, for the exam, you have to know the architecture. That is there because questions will be asked on the architecture.
yeah.
Four architectures are there. One is the RNN, one is the LSTM, one is this encoder decoder, and one is transformer. So these four you should know very well.
Yeah. Will you refer PDF also for that? Great.
Yeah, we will.
PPT, I mean.
PPT I'll give. Yeah, today's PPT also I will upload in that discourse only where the slides discourse is there. Right? There's a post on all the instructor session slides. So I'll just
Uh,
add this up.
don't
Today's
we
I
have
think
that?
week 7 also is left. That also I'll upload.
We don't have that in supplementary contents
For
link.
some reason, I don't know why it is not uploaded on the portal, but there is a thread on discourse. Okay, I've pinned
Okay.
it. The first thread, it's called as all instructor live session slides. You will find all my slides on that.
So I will search your name on Discord and I will
No, the
get.
first thread only of this course. When you just open this course's discourse, the first thread is that only. It's pinned, so you can just open up that. Okay, you'll find it straight away. First one, it is called as all instructor live session notes and slides. Yeah, Disha, any question?
Yes, sir. Sir, I have a doubt in practice assignment of week 9 in one question.
Can you send the portal link once to me because for some reason
Okay,
my
sir.
portal link doesn't work. Yeah. Yeah, thanks, Korang. So let me see. Which question is it, Disha? Can you tell the question name? Number,
The
sorry.
question number 3.
Question number 3. Yeah, this is actually on Q and K. So basically, this is about Q and K. I'll cover it in more detail in week 10. But the idea is very simple. So when basically he's asking you that what will be which kernel is going to give you the maximum similarity. So kernels are basically functions, right? If you remember from MLT, kernels are functions which basically help you to understand data better. So the simple thing for now, which you can remember, is there are two major kernels that we are taught. One is Gaussian kernel and one is boxcar kernel. So Gaussian kernel is normal distribution; it gives us random values. Whereas boxcar kernel is mostly a determined formula-based kernel, which always gives you better similarity scores. That is the basis of this. I think in the lecture in one slide, sir has covered about something about these kernels. But to understand it better, you have to cover week 10. Okay, that will make it more clearer. But for now, just remember Gaussian kernels are more random. So when you want more semantic similarity, boxcar kernel is the one which we use.
Okay, sir.
Okay, but I'll explain it in next week. Okay, so next week we'll discuss these kernels as well.
Okay, sir.
Yeah. So yeah, any other question? Anyone? Any other doubt? Yeah, this is the slide. Yes, Aviral. This is the slide. This is the thread. All instructor live sessions. I think week 7 also I have not uploaded on this, so I'll upload week 7 as well, and I'll upload this week also.
Okay.
Yeah. For week 6 also actually I have slides, like I had planned the slides initially, so I'll upload that as well. So that, and we'll take a session also for week 6, so that we'll complete the slides in that.
Okay.
Okay.
Okay,
Okay
sir.
then, all the best everyone. So we'll meet next week and we'll cover the transformer architecture in detail for the next week. Okay. So thank you. Yeah, all the best. Thank you so much. Good night.
Thank you very much, sir, for the amazing lectures.
Thank
Thank
you.
you, sir.
Thank you. Thanks a lot. Thank you.
Thank you, sir. Good night.
Thank you. Good night.